All right, I'm working on the back panel now, and as you can see, I took the Zabel network off of those two driver boards because that's kind of goofy that they put it on those driver boards and then run wires all the way back to the speaker terminals. So I basically, when I rebuilt this Zabel network, first of all, we went with a little bit bigger resistor and a little heavier capacitor. Same values, just a little heavier. And I just soldered them directly across the speaker terminals. That's really how it should be. And this will get hot. The idea of these is it keeps the high frequency oscillations down. And especially when you're running at high frequencies like at 20 kilohertz, these will actually heat up and they'll get pretty warm. The other thing I did was I connected the new connectors for the power, the fused and the unfused. So you can see one's on one end of the fuse and the other's on the other end of the fuse, and these are your plus and minus voltages. They go out to the two driver boards, and it really neatened this up a whole lot. So that's all set to go, and now we're going to work on the power supply. Okay, the power supply on this thing's relatively simple. So all we did here was just I replaced that 20-watt ceramic resistor that tends to open up on these with a 50-watt metal case resistor. This is for the soft start for the capacitors. It's in line with the transformer, and then this relay will actually short this out after a short delay. And that's what allows the caps to charge up slowly and not blow the fuse when you turn the power switch on. There's 3 capacitors, replaced those, checked all the terminals for tightness. You just want to make sure you go through and do that. We're going to hook everything back up now. I checked all the LEDs, they're all good, because this front panel is really easy to remove. Just 4 screws on the bottom and 2 screws on the top, if I was in frame. 1 screw here, 1 screw here, and then 4 across the bottom. This front panel comes off, and I put a new power switch on it just for good measure, and we're going to give it some power now and test it. Alright, we have the power supply set up for testing, and I'm just going to use a variac to bring this up slowly. If you're using a variac to power this up, you need to jumper out this soft start resistor. So you see I have a jumper across it to kind of take that out of the circuit so that you can actually see the influence of the variac. The other thing is I'm using my variac that has an amp meter in it. I have it set to amps, and we're going to actually monitor the current to make sure it doesn't get crazy so there's no shorts or anything. Another note of caution on these. There are actually 4 power supplies in one here. Each of these 4 big capacitors represents 1 rail of power. So for the left channel, you have a positive and negative power supply. And for the right channel, you have a positive and negative power supply. It's actually like a dual power supply system, except you just have 1 core, 1 big giant transformer, and that transformer actually has 4 separate secondaries. So, and this is a toroid transformer. You can see how large it is compared to my hand. It is a very large transformer, very high current. So it's a good power supply, but very simple. Okay, we now have the first set of power, the left channel power supply set up, or the right channel I should say. I have the amp facing backwards, and we're just monitoring the positive and negative rails. And I had this turned on to, I had already checked the other channel, it's good. But the other thing you need to know is each of these big capacitors has an 8.2K bleeder resistor across it. So you have 4 bleeder resistors, 1 for each cap. But even with that 8.2K bleeder resistor, these have such high capacitance that you can see this has been off for about at least 5 minutes, and there's still 15 and a half volts on these capacitors. And you can see it is slowly draining it down, but you can't just turn this off and reach in there. There is plus and minus 80 volts. There's 160 volts potential between the two DC rails there, and it takes a good 15 minutes to bleed all the way down to 0. So this is not an amp you can just go jump right in and start working on after you turn it off. You have to give it time to discharge. So let's turn the variac on, and I can tell already that from the residual voltage there's no shorts on this channel, but we're going to power it up anyway to full power and see what we get. And you can see and I'm monitoring the current on the amp meter, and as long as I turn it up slowly, it's only drawing milliamps. And at about 48 volts, you just heard that little click, maybe not, if the mic picked it up. That's the soft start relay coming in. So that works. And if we go all the way up to about 120 volts, we should see somewhere around 80 volts on there, and there it is. So we have plus and minus 80 volts. So all four now of our power supplies, all four rails, are good. So let's turn this off, and you can see I've just killed the power, and you can see how slow this is in draining. So just be extremely careful when you work on these. These have a lot of current and a lot of voltage. Okay, we have the amplifier all assembled here, and let's move in and take a look. Now there are quite a few wires that need to go in on this, and one of the things you want to make sure you do is there's 4 heat sinks here. These are the upgraded ones for the new board. Hold on. And if you compare them to the old ones, this is just a little bent piece of aluminum. And these are much thicker and taller. And even with this, these still run very, very warm. So if you notice, when you put the wiring back in, you kind of want to get things zip-tied out of the way. See how I kind of made it go down the middle with the wires? And all around in here, if you notice, there's like an air pocket area to let the air kind of vent up a little bit so that these will run as cool as possible. Now we're going to go ahead and power this thing up, but I have a feeling we're going to have some problems with this. On this particular amplifier, every single transistor that could be bad just about was bad, even to the point where the bias control transistor was bad. And let me show you where those are. So if you look on the amplifier board, there is a hole actually drilled right into the bottom of the board, and there is a hole drilled into the actual heatsink material. And in here you can see that white stuff. There is a transistor stuffed in there upside down and then glued in. This transistor was good on the left channel. However, on the right channel, that transistor was shorted. I don't know how, but it shorted. Now, trying to dig that out, that glue was so hard you almost can't get it out. You almost have to drill it out. I did put a replacement transistor in there. The pinout was different, so I had to swap the wires around. The 3 wires are right here, and they go over to the driver board. So the bottom line is I did not have an exact replacement transistor. The transistor in here, it's a 2SC, I think 3478, and it's a very difficult one to find. And there's very little information online about suitable replacement. I tried a transistor that I had that the characteristics matched up, but that almost never works. So we're going to try it. If this side won't bias up, that's almost certainly going to be what the problem is. And we're going to have to try some different transistors and try some methods to find one that will work. I'm hoping I'm hoping it works. If it doesn't, oh well. Of course, the whole thing might go up in smoke. Who knows? But let's apply some power to this thing, and let's see what kind of bias we get and if it works. Alright, we got quite a mess here. I have a meter connected to this side, and this is the set point for the bias. and I got a meter on this side. I have my amp clamp on the incoming line, and I have a big variac here that can actually handle the current of this thing. I have the soft start resistor jumpered out, and we're going to just slowly apply power to this. And the first thing we want to see is just if this thing powers up. We know the voltage is there and everything. If we get crazy current, we pretty much know that there's a short here somewhere. If we don't get crazy current, and then we see some bias coming up on the 2 voltmeters, then there's a good chance that the amplifier is going to work. So we're going to monitor all this very, very carefully. We have fuses in everything, and sometimes what I'll do is the fuse for the variac, I will actually put a much smaller fuse than this calls for. If I'm not going to be running the amp at high power, you can put a 1/2 amp or a 1 amp fuse in there, and any kind of surge or any kind of short will take out that fuse before it damages the amp. Just another trick you can use. This is not really a good candidate for using a dim bulb tester. These amps don't really like this because of the servo circuit, and we'll look at the servo circuit here in a minute if this thing turns on. We'll go a little bit into that before we go any further. All right, let's go. Turn it on, see what we get. Okay. See if we can. Went up to about a 1/2 amp, and we're sitting about 30 volts going in there so far. Let's just keep bringing it up. And really what I'm looking for is this doing a big jump in amps. I wouldn't expect this thing to idle too much above 1 amp or so. Okay, there went the soft start relay. Had that resistor been in circuit, it would be shorted through now. And we're still holding right around 1 amp. And as we're turning up the power, those 4 great big storage capacitors are charging up. All right, well, we got about 90 volts on there right now. So far, so good. And we do have some bias, and we want to see about 25 millivolts. And you can see, good news is we do have bias on both sides, so maybe my transistor substitution is going to work on that one channel. So let's continue. And should be just about up there where we need to be at full power. And there we are. So we have about 120 volts going into the amp now. We are drawing about 1.2 amps of current. I think that might be a little high, but maybe not. And looks like we have 22 millivolts, which is really good. So the left channel, the one with the original bias transistor, is almost spot on. It needs to be 24. The other channel is 11 millivolts. So to adjust our bias, you just turn this little pot here for each channel, one there and one there. This is the channel we want to try to adjust and see if it does anything. So let's put that in there. And we want to look at the blue meter, the bottom meter. Let's see if we can get that to go up to 24. That's going down. Nope, that pot is maxed out. So that's as high as I can get the bias to go on this one. So that tells me our transistor is not appropriate for that circuit. We need to try a different bias transistor. I mean, we can adjust it down. We just can't adjust it up any higher. So now the game begins to try to find a bias transistor that will work in the circuit. So I guess the good news is at least the amp is working. The current is not going up any. It's sitting real stable at that 1.2 to 1.3 amp range. I don't smell any smoke. And our bias is pretty much staying right where it's supposed to be. So we may have to mess around with that bias transistor and change it. Okay, I now have a signal generator connected with a 1 kilohertz tone, and I'm going to drive about 100 millivolts into this, which is not a real big signal, but it's a decent signal. And I have an 8 ohm dummy load, and we're just going to see if we even get anything out of this. So let's take a look and see. Here we go. Hey, how about that? Right there. So 2.27 volts. So that's only, not very much power, but just enough to know that the amp is working right now. These are warm. And they do get rather warm, but that's the way they run, I guess. The outputs, ice cold, which is good. They're idling real well. And yeah, I know you're going to turn off. So we'll pull this out. So other than these being running really, really warm, which is to be expected, everything seems to be okay. Other than the bias not being high enough on the other channel. So that's all good news. Sounds like it worked right out of the starting gate, with the exception of one little problem, and that's that goofy transistor. So let's see what we can do about that. Okay, we're now running an extremely small signal to the tune of about 1.8 milliwatts into the 8 ohm dummy load. So it's it's a 1 or just under 2 milliwatt signal. And you can see the influence of the servo. This is the good channel with the original transistor in it. And you can see that this is offset. In other words, you can see here's your 0 volts, and you can see the offset. But you have a perfectly clean sine wave even at 1 milliwatt. There's no crossover distortion, nothing. It's holding it perfect. But you're getting a little bit of DC offset. Now, this is only millivolts of DC offset. It's not going to hurt the speakers at all. But if you notice this one, the servo's actually holding this one much better on the channel with the replacement transistor. But if you notice all of this noise, and again, I believe this noise is coming from that substitute transistor I'm using. Now, this noise probably would not be audible to us because this is such a tiny little signal, and as soon as you turn the drive up a wee little bit, it straightens right out. But you can see there is a difference between the two channels. So I just thought that'd be an interesting thing for you to see. But what this means to me is that we can turn this amplifier down to a whisper and still get very pure, clean sound once we get this all straightened out. And that's just as important as an amp that'll crank and make your ears bleed. You want the amplifier to sound good at all volume levels. So I think this amp's going to be awesome once we get everything tweaked in. It's been running now for about 20 minutes. The amp is, I can feel the transistors are now, the heat sinks, you can actually feel that they're above room temperature, but that's all. The drivers, they've kind of leveled off. And, our bias is rock solid. All right, so I have the amplifier turned off now. I thought I'd share a little bit with you about how this amp works. So if you notice, these two rectangles here, right here, this outline here and this here, each of these represent these two power output boards. So the NPN section and the PNP section. That's these two circuit boards. And on that circuit board, you can see one of the two boards, you actually have this transistor. And notice it's really not connected to anything in the circuit. It's just on this board, and this is where that hole is drilled through the board, and it's attached to the heatsink. So this is thermally coupled to the output transistors. Now, if we go back to over here to the preamp section, let's get back a little bit. You can see where this goes into J106. So here's J106, and this is that pot we were adjusting for your bias, and that bias circuit will find its way back through the feedback all the way up to this little op amp, and this op amp is what's called a servo. If you notice, there is no DC offset adjustment. Any of you who've worked on amplifiers know that there's usually two adjustments that you make when you set up an amplifier. One is going to be the bias, which is kind of where you're setting your transistors to just be turned on, so they're in their operating point, and that eliminates the crossover distortion. But there's also an adjustment called DC offset. So if you notice, there's two of everything. You have, in other words, you have two sets of the outputs. You have, and this is called push-pull. And the idea is both of these banks of transistors need to be turned on the same amount so that the resultant voltage between them at the center point is 0. If there's anything, either one of these sides is turned on more than the other, then this will not be 0 volts. It will favor whatever the negative or the positive voltage side is that's turned up higher. So that we call that DC offset. In a perfect world, this would be 0 volts with no signal. And only when you apply a signal, when you turn your music on, will this fluctuate up and down. That's what makes your sound. Now, all of that is influenced by all of this. And if you notice, these are those very closely matched transistor pairs at the very beginning of our preamp. And these little differential pairs, if they are not matched and they are not biased perfectly in the middle, it'll carry all the way over and throw off our output. Now, originally, or typically, the way you would see this is somewhere around in this section, there would be another pot, and it would basically create a little error voltage between the two sections that allows you to balance these out to 0 volts at the center point. But this particular amplifier uses what's called a servo circuit, where you have this little op amp, and it acts as a self-adjusting potentiometer, if you will. I'm just kind of making up a term, but to give you an idea as what it's doing. So you can actually see the influence of this as the temperature of the transistors change, as the signal changes in here, as capacitors charge and discharge. You'll see the influence of this, and it will kind of, you'll see that DC offset will creep a little bit, and then it'll creep back down. And that's the influence of this circuit. So all this stuff kind of has to work together. And if this transistor right here does not bias properly, it throws everything else off with it. So by choosing a different type of transistor, that's what I was talking about, that you have to get one that's really has the same characteristics. And this is kind of a bit of an oddball, the type of transistor they're using. It's not just a standard off the shelf. First of all, it's rated at 200 volts, even though it's a tiny, teeny little transistor. So right there, you limit yourself how many options you have, because there's not a lot of small signal transistors that are 300 volts or more. Then these also have relatively high gain, and usually high voltage transistors like this in these little packages don't typically have a high gain. So yeah, good luck. So we're going to keep experimenting and try to figure that out and see if we can get that other channel to be just as perfect as the other one. Well, winner, winner, chicken dinner. I found a perfect transistor that'll work in here. I am using a KSC 2383, and it's perfect. It's absolutely dead perfect with this transistor in here And yes, it is kind of ghetto right now. I got it cobbled in here. But if you take a look, there it is, hanging. But right now, sitting out in space, just tacked on right around the center of travel of that adjustment bias pot, I get my perfect 24 millivolts. So what we're going to do is, because it's so difficult to dig the transistor out of that hole, because they actually have it glued in there with thermal glue, what we're going to do is both boards, both sides, the top and the bottom board, both of them have the hole drilled in it. So if you look inside here, you can see this is 3 brand new pads, never been soldered on. There's a hole in the heatsink and in the board. So all we're going to do is we're just going to transfer these wires from this upper board up here, that used to be up here, and we're just going to transfer it down to here and mount it onto that board. Again, it's all the same heatsink. The temperature the temperature will be the same. It will work the same, and we don't have to try to dig that transistor out. We'll just use some of our thermal adhesive, put it in there, and everything will be good to go. Okay, I hit the record, and the record didn't record, so I'm going to redo this all over again. So what I'm going to do is I'm going to show you the influence of how this transistor operates as the bias control. So what I'm going to do is we're going to look at the bias voltage right now, and I'm going to just take my fingers and warm the transistor up by pinching it between my fingers, and I'm going to show you how this works. So here's the bias, and you see it's kind of creeping up a little bit. Now watch what happens when it heats up. There, I just grabbed it with my fingers, and you can see how it drops down. And as I let go of the transistor and I wave my hand and just fan it, cool it down, you could see the heat goes back up, or the bias goes back up. So that's how a bias circuit works. So this is going to be thermally coupled to the heatsink. So if we look up here, here's your heatsink. Now on these boards, they're identical. And the one up here is where that old transistor was mounted, and it was a heck of a time trying to dig that out, because that glue that they used to glue the transistor thermally into the heatsink was very, very hard. So what I'm going to do is I'm going to just transfer everything over to this other board. Both of these boards are mounted to the same heatsink, so it really doesn't matter which side we mount that transistor, and it's designed, if you look down in here, here's a hole, here's the 3 solder pads, here's the place for the wires, everything to mount the transistor. So we're just going to move it over to that side. Everything's going to be good, and this amp will be ready to go. So let me get that done, and as soon as I do, we'll be back. Okay, as you can see, there's our capacitor, the shunt capacitor there. And right there's our new transistor, and I have to wait till the thermal compound sets up a little bit, because it's kind of runny for a while till it hardens a little bit. But it's mounted in there. I transplanted the wires from the top board down to the bottom board, so you can see them coming out of there, the red, yellow, and blue. And we're powered up, and it's been sitting for a few minutes, and look at that. Perfect. Perfect, perfect, perfect. So I'm just going to let this sit and cook for a while, and then we're going to go and give her test and see how she runs. Okay, now we're doing our 1.8 milliwatts into 8 ohms test again, for our really, really low power test. And if you notice, they both have about the same amount of noise on them. They're almost identical now. So everything's looking good. The only thing that I did notice is still that one channel has a little tiny bit of offset from the servo. That could just be that one of the transistors is a little bit mismatched from the other. Not bad, but Again, this is as soon as you turn the power up a teeny little bit, that straightens out. So now let's do some more tests and see what kind of power this thing puts out. Okay, I've been doing a few tests on this, and I'm using my times 10 on my dummy load, so 5 volts per division is actually 50 volts per division. And let's turn this on and see what we get with the full 2 volts RMS input. I think that's what you need input on this amp to get rated power. So let's do it. 45 volts. 45.1. So 45.1 comes right out to 254.25 watts. So, and it was just starting to clip right there. So the amp is working perfectly. I started ramping it up a little bit on my 1800 watt isolation transformer, and the transformer started to sag. It couldn't take all the power, so I had to direct plug it into the wall, which is not a problem on this. So looks like this thing's working good. Let's check some distortion. All right, let's start this thing up at full power and then take a look at the distortion. All right, 0.01, and that's at 254 watts per channel. I would say that's pretty good. All right, I'm thrilled. I can't wait to test this thing. So now there's nothing left to do but kind of do a burn-in test on the bench for a while, make sure everything's happy. And I have to admit, I'm pretty surprised that we only had one little issue. That was a major project, rebuilding all these boards and doing all this stuff I've never done before on one of these. So I think I got to give credit to hoppysbrain.com. They have a fantastic product. It works as advertised, and I am completely thrilled. And I am going to email them and let them know how much I like this product. Okay, let's do a square wave, and really I'm just kind of looking for ringing at the big leading and trailing edges here. So I'm not going to run full voltage on this. I'm only putting about 1 volt RMS, so it's about half drive signal. And I just want to see, and that is a very nice looking square wave. And if you look at the rising and falling edge, no slope at all, so very good. Now, you don't want to drive a square wave into these amps a whole lot. It's very hard on that Zobel network, and puts a lot of heat on the amp, but actually with all the upgrades to this amp, it can take it a lot better than the stock amp. These amps really had a lot of weaknesses when they were new, but I think some of our mods that we made have overcome that. So let's look at some other things. Okay, now let's try a frequency sweep from 0 to 20 kilohertz and see how that looks. Looks pretty flat. Nice. All the way up to 20K. All right. Okay, we're now set up to check channel 2. Let's see how it performs. And it looks the same as channel 1. Nice. All right. Okay, I now have channel 1 and channel 2 superimposed over one another. So you can see there's 2, there's 1. And I have both channels driven with the same sweep signal And what we're going to look at is to see if the two channels with the same input track the same. So let's do that now. In theory, we should never see those two signals separate. Here we go. And you could see little teeny tiny bit of blue right there. Just the tiniest little bit. But you could see they're tracking perfectly with one another. No distortion. So that's actually a good thing too. And I'm kind of driving this amp just medium. You know, I'm driving about 60 or 70 watts into it, into the dummy load. So I'm not driving it real hard, but that would be a very loud listening level in a normal room. And you can see it's performing very well in the amp. The heat sinks are just getting barely warm. So this is all very good so far. All right, our next test is going to be a little bit more difficult. We're going to do the same sweep, but we're going to do this superimposed both channels with a square wave. So let's see how it handles that. I'm looking now, we're looking for ringing, any kind of ringing or any kind of bad oscillation or anything like that. And you can see at the higher frequencies, it starts to, you can see it kind of starts to get a little bit of ringing to it, but not too bad. And I'm not going to run that real hard because that's really hard on the Zabel network. But you can see at higher frequencies, you get a little bit of slope. But still not bad. All right, last test. We're going to run this thing full power output, sweep it from 0 to 20 kilohertz. And I'm only going to do this one time because, like I said, this is really hard on the outputs and on the Zabel network and everything. Here we go. And I have both channels superimposed over one another once again, as you can see. It's holding pretty steady. All right. And the dummy load's even getting a little bit warm now. Okay, so there it is. Really, there's nothing left but to listen to it. All right, let's see how this thing sounds. We got it all connected. All right, well, I think this video is getting long enough, and I'm definitely getting tired. It's been a long week, it's been a long month with work and everything, but I'm really happy with the way this amp turned out. So I hope you all enjoyed this as much as I did, and I wish you all, as always, peace, joy, happiness, and good health in your lives. Happy holidays coming up here, and I wish you all the best. And until next time, be well and take care. Bye-bye.